Okay, welcome everyone to another CTMP installment. Today we have a very exciting speaker that I'm sure you've never heard of before. Very, very exciting. Just kidding, but this is our very own Heribert Weigert, who will be telling us about the notation, the useful notation in QCD. And this is Birtracks. It's called Birtracks on the fly. So,
all right, let's get this going. Right. So this talk is meant to provide a skeleton for an introduction to Birtracks and their use in QCD generically. The goal is that at the end, you have a chance to recognize Birtrack expressions and interpret them on the fly. That's the idea. And let's hope I'll manage to do that. So I'll first give you a little bit of context. Perturbation theory in a confining field theory is one of the motivations to use this in QCD. That is all about color singlets and the fact that confinement means there is no color observable in the universe. And in order to talk about this, you need to know about states that are color neutral. And those we're going to get out of Birtracks. There are many tools that you need to do that. You need to have a bit of an idea of the most elementary representations of QCD symmetry group, namely SUN, and the N for QCD is NC, and in fact 3 therefore in nature, but it helps a lot in deriving expressions and understanding consistency to keep N generic and arbitrary in your calculations. I will then get to the point of talking about Birtracks, both for the permutation groups of N objects and SUN. In general, we'll talk about primitive invariance and then get to irreducible representations, a certain subset of irreducible representations of SUN, and then come back to the motivation a little bit and point to how that feeds into this. All right, so what's the motivation for me to get into this? Well, it's actually 2 types of observables that I connected with. The ones that you see a picture of on the left, those are jet events in collider physics. So you imagine you collide 2 beams of particles into each other, and if you have a hard collision, a collision in which you deposit a very high energy, and this does happen very often at the LHC, you will produce particles that individually carry a lot of energy and a lot of momentum away, and that leads to a phenomenon that an event looks like the one that you see with the black background in false color, where you have sprays of particles that come out in a very directed manner, whereas most other stuff does not have as much energy and doesn't penetrate this far into the detector. That's what we see there. The other side comes from deep inelastic scattering. That's abbreviated as DIS up there. That is the type of experiment where you say take an electron and you hit a nucleus with it, or a proton in the simplest case, and you transfer so much momentum onto it that you shatter the whole thing and you break it to pieces. Now, whereas the first sort of events are events where you look at particle production generically, in DIS, you actually look at an inclusive cross-section. You don't at all discern the details of the final state. And in that situation, at very high energies, at the extreme end that you can reach, you get to see a picture of the object that you shatter there, that because of quantum fluctuations looks like it's filled to the brim with quarks and gluons. If you do this at smaller energies, These are the pictures, little pictures to the left. At very small spatial resolution, that's what you transfer onto this when you shatter that thing. You see 3 quarks. And the harder you hit this, the more stuff you get to resolve. And if you do this in the stream case, you reach a situation where it looks like it's full up of colored objects. And that means, of course, that you cannot treat them as totally independent objects. You will expect complicated things like correlation lengths to pop up. If you have a piece of probe, right, that hits this dense mess over here, it will just see the dense mess around it instead of any other piece of the probe that you send through this a little ways over there. Can you see? Yeah, you can probably see the point of it. Funny thing is, that's the picture in the middle. That shows the kinematics in which this happens in a space-time plot that throws away one of the directions. So you have the collider axis, which is actually not marked. Time goes upwards, and you see a light cone and a tangent plane. Jet events essentially have their emerging particles move along the forward light cone there, come out with the speed of light, right? Enormously high energy compared to the masses involved. So essentially light-like trajectories. Whereas in the DIS situations, you see things that happen in the backward tangent hypersurface to the light cone. And funnily enough, you can map one onto the other using a conformal map. That's not the topic of today's talk. That just gives you a hint that these things are related in a way and amenable to similar treatment. The issue in calculating cross sections in these connections have to do with which cross sections that experimentalists can measure almost anything by counting particles, right? A measurement doesn't care about the confining properties of QCD because nature takes care of this, and then you measure the outcome. If you, on the other hand, want to compare that measurement to theory, you need a way to calculate the same thing. And that's where the subtleties come in, because if the observable you have is sensitive to long-range physics, long-range physics is where confinement comes in, and where things become untreatable in perturbation theory. That's where the coupling constant becomes small, and any attempt on expanding things out in a perturbative series, even if you try to sum it, is bound to fail in that situation. So in order to select observables where you can compare to analytic calculations, you want that those observables to be selected in a way that you can actually calculate it. It doesn't mean that the theory can't describe it. It's just that we cannot apply the theory in this situation in a way with standard tools in order to connect up to experiment. So there are two things in observers like this that are absolutely important. One of them is collinear safety. That's pretty obvious in the jet situation. What do you mean by this? You have these jets come out in different directions, and if you look at how you calculate this on the level of quarks and gluons being emitted, right, one after the other. And at the very end, they turn into hadrons. Out there at the end, essentially out there at these where you measure them at the detector, they have been converted to hadrons. Now, believe it or not, it's not so totally easy to describe or to prescribe an observable, a measurement procedure, in which your perturbative expressions that have, say, n of these jets in there reduce to the same to your perturbative expressions where you have one less in there, which you could easily achieve by, say, taking two of these and move one one of them in angle until it aligns with another, right? So these observables must be constructed in a way where you safely recover the one less sky in their limit. If that's not happening, this is a surefire way of making non-perturbative physics influence the observer. The other thing is infrared safety. That's emission of zero momentum particles. That should reduce, and a zero momentum particle is nothing that comes out, right? Zero full momentum means it's not moving anywhere. So that must look like your perturbative expression for a cross section that has one less particle in it. And if these limits don't work, you can't calculate the perturbative. That's a big issue. And the question of how to judge whether this works or not on a deeper layer has to do with understanding the color neutral states in QCD. So that's the background and why I got interested in this sort of thing. Right. So for this, we need a couple of tools. And the first thing is you need to have a relatively clear idea of what the symmetry of QCD is. The symmetry group of QCD is SU3 for color, but in general, right, this is a Lie group. That is a group that's a subgroup of the group of invertible matrices. This is GLNC, GLN over here, that has a couple of additional constraints imposed, namely that its elements be unitary and have determinant +1. So the group is really defined by its action on Cn as a matrix group in this case. Such groups possess an associated vector space that is called its Lie algebra, and an abstract definition would be something like it's all those n by n matrices that, when exponentiated with an arbitrary real factor, this is this S that sits here, and by exponentiated I really mean just the exponential series of powers of the matrix S X with the prefactor S in the appropriate spot, and such that you end up in the group. So this condition is actually very easily converted into a condition on that matrix. That condition simply is that these matrices have to be anti-Hermitian. This is condition 1 over here, and that the determinant B1 translates into tracelessness for those matrices. It's pretty easy to check that these matrices form a real vector space. Now, irrespective of the fact that the matrices themselves have complex entries, the vector space must be real, because, like, imagine you have an anti-Hermitian matrix and you try to form linear combinations, and these prefactors have imaginary parts in there. Taking the complex conjugate when you conjugate these guys, it's going to mess with the anti-Hermitian, right? Trace condition is also not hard to get. If you check this out, you find pretty quickly that this is, so it's a real vector space. I think I have explained this. Its dimension is n squared minus 1. I'm not going to get through this, but this is not hard to obtain. And I called it an algebra. So what you're missing is a product. There is a product in this, and that's simply the matrix commutator. The matrix commutator of two of these such things automatically satisfies the same conditions. And since it's a vector space, finite dimensional vector space, I can always write the basis. And the interesting thing is, it inherits essentially an inner product from Cn. And it becomes a real inner product. And I can therefore choose a basis of orthonormal matrices. These guys are usually referred to as the generators, and they carry a label, right? A labels the various matrix elements, and then I can capture the behavior of any element by having a look at how these basis elements fare. For example, under the commutator, and those are the famous commutations, I have the I in there because there's a dichotomy between making visible that this is a real vector space for which you need anti-Hermitian matrices, and the physical literature, which prefers Hermitian matrices because they have real eigenvectors. That's why I have an extra I in there. The TAs that sit there are Hermitian by the simple expedient, right? Because prefactor of I turns a Hermitian matrix into an anti-Hermitian matrix. So this is just to make it clear that this is a real vector space, because what this commutation relation says is simply the commutator is again such a matrix, an element in the vector space, and it can therefore re-expand the commutator in the spaces with a bunch of real coefficients. And here you see the real coefficients, the structure constants in the game. Okay. I need two more ingredients, and then I'm done with my mega short introduction to SUN. That one is the adjoint representation. That is a way that allows SUN to act on its own Lie algebra elements, and they simply act by conjugation. And it's very easy to show that this Lie turns Lie algebra elements and Lie algebra elements, that the transformation is linear. It's actually an orthogonal. Well, you can, given your basis of generators, even show that this is an orthogonal transformation. Right? The last ingredient I need here is that it also acts naturally on the dual space of the vector space that you worked on. And this is simply done by looking at the dual vectors, the transpose complex conjugate vectors that you would act on normally by multiplying them from the left with u's. You turn them into the columns into rows, and then you act with your dagger to the left, or equivalently, if you want to act on the right, you just transpose this equation and look at what you see there, and you talk about complex conjugates. Those three ways of let SU3 act are independent and non-equivalent, as in there is no similarity transform that takes the matrices in one representation into those of the other. And in fact, you can take the fundamental and the underfundamental and take tensor products and create all arbitrary irreducible representations of SUN. And I'll say a few more words about what irreducible means a little later, if that's not something that you're familiar with. Right. So, shortest introduction of SUN ever. Let's now get to Birtracks. The first thing we know, we need to talk about Birtracks. This is the first place where you would introduce them naturally, is actually the permutation group, the group of permutations of n objects. So to introduce this, you would take a set of n objects. The simplest set of n objects is the numbers 1 through n that I've written down here. And then the permutations are simply all bijections of this set. Means all reorderings of this set, right? That don't repeat anything. So there are n factorial of those, and there's an easy way to write this as permutation lists. You write your set, right, in the first row, and underneath it you write the list of objects that you obtain when you apply your permutation. So there's an example on the right. Right, you start off with 1, 2, 3 as your list, and you turn it into a reordered version of this list. 3, 2, 1, for example. This is a permutation. Clearly, there are 3 factorial 6 different ways of doing this sort of thing. But there are other ways of writing down permutations. One, I hope you've seen before, that's the cycle notation expressed in terms of these brackets here. This is in cycle notation the identity operation that says take 1 and leave it be, take 2 and leave it where it is, and take 3 and leave it where it is. This is the identity permutation. Mathematicians very often don't write one cycles in the notation, but I added them here to make it explicit what they're doing. A cycle that has more than one thing in there means that you take the first element, turn it into the second, second into third, and the last one goes in the place where the first one was. So the one that you see on the right over here is a permutation that takes 1 into 2 and 2 into 1. So it swaps 1 and 2, and it leaves 3 where it is, and you see what it does as indicated there, and all the other ones work the same way. I can write the same thing in terms of Birtracks. Birtracks have the advantage of immediately making this visually, what happens visually, visually explicit. So I take a permutation of 5 objects down here. This is copied right out of Judy Zeilinger's lecture notes on this. And you first write columns of the objects, 2 columns of the objects that you have in one direction, and to mark the places where they go. And then you draw lines to show where the elements go. So 1 goes on to 3, right? 3 goes on to 4. You just follow the arrows, goes into the 4th position. You just follow the arrows as they are, and then you just retain the lines, and you have a representation of your permutation as a conglomerate of lines that tell you which position goes where. Just to give you, say, the permutations of 3 objects, and as a set in terms of Birtracks, you see that my sources for the diagrams were various, so they're not all looking exactly the same. The arrows appear in different places. I have to clean it up a little bit, but it's clear enough what it is. You see here the identity permutation, a permutation that swaps the last 2, a permutation that swaps the first 2, one that takes the first 2 1 notch down and the last one up. You can convert back between those representations pretty easily. What is really neat about about Birtracks that it's very easy to write down composition of permutations. You see here 2 down here, the product of 2 permutations. This one is that guy, and this here, right, is a swap of first and last, and you just connect them by connecting the lines and following the lines through. And once you follow the lines through, you end up with this permutation, right? Very directly and pictorially. Very hard to make a mistake that way. Inverses are also easily obtained. All you do is you reflect your diagram, and then you reverse the direction of the arrows, and you have the inverse. That's pretty obvious why this should be the inverse, because you're just following now, right, the arrows backwards from the other side. It's clear that this should be the inverse, and that's pretty easy to check in examples if you want a little more convincing. Now, this in it by itself, having the permutation group act on just n numbers is a little boring. I mean, you can do a lot of math on this and learn a lot about the group and its structure, but we use this in physics in other ways. Use it in physics to act on the components of tensors by permuting components on tensors. So Sn acts on an n tensor by swapping the components around. And I can very nicely write this, of course, by throwing in a bunch of Kronecker deltas that tell me, okay, this index goes into that index, and what you see the permutation appear right up here in those places, right? Very nicely. And what you see that way is that, okay, what you're actually carrying out is a linear map on the tensor space that fiddles with components. So, in fact, this provides an injection as a group isomorphism of the permutation group into the linear maps on our tensor space. This is a representation, if you wish, of the symmetric group of Sn, the permutation group in n objects. Interesting enough, right? Let me just take an S3 example and write the same thing as Birtracks. This is what the Birtrack instructs you to do, and now you see, oh, this is just a bunch of product of corrlators that you can express this way. And of course, I can now write my operation of the Birtrack, which I know just represents a bunch of corrlators, and just leave all the indices off. I know, right? I know that this combination of Birtrack acting on a tensor just means I've swapped around the indices in this one. Right. Now it gets interesting because now I'm going to link SUN and the permutation group together. Imagine our vector space carries the fundamental representation of SUN. So I know how I add SUN elements on this vector space. So in this case, I'm essentially saying my vector space is isomorphic to Cn. Then I know the tensor space inherits this action simply by saying, okay, it acts on the tensor space by attaching a group element of SUN to each of the indices. Any which in this index picks up a factor of u, and in component notation, this is what this looks like, right? Linear maps on this vector space pick up factors of u and u dagger on the left, u's on the left indices, u daggers on the right indices. So let me take one of those things up there, one of those A rows explicitly. This is written down here. It picks up factors of u on all the left indices and u daggers on all the right indices. And if you look at this carefully, you see, the Kronecker deltas just connect these into u times u dagger. But since this is SUN, u dagger is the unit matrix, so what you get back is Kronecker delta. So this shows you that these linear operators on the tensor space, in fact, are invariants under SUN. Right? And because the reason is so simple, they're called the primitive invariants. This is not rocket science. This is just being able to play with tensor indices properly. Right. Let's look at a very, very simple example of what is going on. Again, the diagrams are not ideal, but what you see in terms of Birtracks here is leave the indices sit. This is the first Birtrack here, and the second Birtrack is swap the indices. I take a tensor with two indices that I'm acting on, and a tensor with two indices is a matrix, right? Nothing complicated. And of course, I can leave the indices in place and swap them. But if you look at this, this is what I've done actually is the identity operation, but I've separated things out into a piece in which I add leave indices B with swap them. And here is leave indices and swap them, but subtract the result. Right? What this secretly does for you, because it's a linear operation, I can actually write it like this. The first piece here has its indices symmetrized. The second piece has its indices antisymmetric. So what I've done is I've picked out the symmetric part of the matrix and the antisymmetric part. The operations I call a symmetrizer into indices, and the other thing I call an antisymmetrizer into. So what you see happening here is that these linear maps, right? Well, linear maps, I've read this as a linear map on my tensor space. In this case, on the tensor space of the matrix. And I form linear combinations, well. Linear maps clearly, right, form a vector space, so I can form linear combinations. That's absolutely legal. but they also form an algebra because I can still form, right, form compositions of these linear maps on these linear operators that I'm working on. In the math literature, this often comes in as the group algebra, formal linear combinations of the permutation group elements. For us, this comes here as formal linear combinations of operations on tensor spaces, and that brings in additional structure. I've already talked about, right? Since this is a linear map on tensor spaces, it's a linear map, and linear maps have trace operations associated with it in a natural way. In this case, the trace is really something very, very simple, something where I go close up all the lines in, say, this on this primitive invariant on this particular permutation example, which just means that I set the first index and that I multiply this with a Kronecker delta to close up the line, right, and contract indices on the left and on the right. And you can actually calculate this very easily, just graphically. You just look at wherever you have a closed loop, there you're calculating the trace of an identity matrix. That gives you the dimension of the vector space. And if you look at this example here, you see two closed loops happening. One is the little one here, and there's a second one out there. You start here, you follow this all the way through the crossover here, but this is one closed loop, and you end up with dimension of our vector space squared, dimension is n squared. Right? Visual computation. You don't need to actually carry out operations on Kronecker deltas. You just look at the diagram. It also because we're talking about these linear maps on V to the n, we inherit the inner product if V had one. And what this turns into is actually just a multiple of the trace operation as listed here. Any two such tensor operators, linear tensor operators, have an inner product that is given by this trace. And you can always stick a real overall prefactoring that's just convention. And that's chosen in different fields in different ways, so I leave it generic here. You also get, once you have an inner product, you can also talk about Hermitian conjugation. And in this situation, Hermitian conjugation, if you look at what is going on here and draw a couple of examples, you see that it actually amounts to reflect the diagram, if you have a Birtrack diagram for this, and reverse the errors. Well, that's a procedure that we've seen a little earlier, right? For a permutation, that is just the inversion of operation for an individual permutation. So what this does is we have a representation for the permutation group on these tensor spaces that is actually unitary with respect to this particular inner product. So these are structures that don't have on the group algebra. For this, I need to have a representation on these tensor spaces where I'm getting all those extra ingredients from my vector space. So that's why we have all these extra tools available when we do this in applications PCB. So what we've seen here is now an algebra, right? An algebra of linear combinations of these tensor operators. And this thing contains subalgebras as in subspaces that are closed under composition, under multiplying these things together. There are two really obvious ones. One is the total symmetrizer, which is a very simple linear combination. You just add up all of those permutations and divide by the number of permutations that we have there, because that combination itself is a projection operator in the sense that if you square it, you get the thing itself, the operator back. This is plausible, right? You symmetrize something in a bunch of indices, and once it's symmetrized, if you do it again, nothing happens. There's another obvious one, the total antisymmetrizer, where you also add all of them up, but you flip the sign depending on whether the permutation is an even or an odd permutation, whether you can factorize it into an even or an odd number of transpositions, pairwise exchanges. That's pretty easy. And that thing also is a permutation operator. It antisymmetrizes it, right? It means that once you've applied this to a tensor, swapping a pair of indices always gives a sign. And you can easily check that this again is a projection operator. So if you take this to generate the subalgebra by forming powers, you end up with a closed algebra that contains precisely one element, in the symmetrizer or the antisymmetrizer. Right? Those guys are actually mutually transverse. That is, product of a symmetrizer with an antisymmetrizer always gives you a zero. And if you look at this very carefully, you will actually also see that these are Hermitian operators in the sense of this inner product that I had introduced. But in general, there are more than these two trivial guys that have one-dimensional subalgebras in there, and that is governed by something that is known as Young collisions. Now, you may or may not have seen this before. Now, this is the introduction by example method that I'm going to throw at you. I'm not going to give you a theory here because that's a lecture series. But at the end, I will give you a reference. Julie Alpert-Salinger has made very nice lecture notes on this, and from there you can get the theory. Let me just give you an example. So a Young diagram that is a collection of boxes where you draw boxes in a way that there are always, you have rows and you attach rows underneath in a way that the top rows, the following rows below are never longer than the rows you have above. They can be as long, but never longer. You have for Sn, you will have always precisely n boxes that you can put into a Young diagram. And Young tableaus you get from starting to label those, and you are only allowed to have labelings in which the integers with integers from 1 through n, and the integers can only grow as you go from left to right, and they can only grow as you go from top to bottom in a column. That gives you a calculable number of Young tableaus that are, these are the numbered diagrams. And from those, you can construct your tensor operators in ways that in which lines that have numbers that fall into a row are always associated with a symmetrizer, and I draw my that I should have said, I draw symmetrizers always as lines, right? This is a symmetrizer for 3. I draw this as something that has an empty box and an antisymmetrizer that has a black filled box. And the identities that I had written down before for symmetrizers and antisymmetrizers now in Birtracks look like this. This says antisymmetrizer is Hermitian. That says symmetrizer is Hermitian. This is they're mutually transverse, and this is their projectors. The square is the thing itself. And one of these was meant to be symmetrizers, so I have to fix this in the uploader. So here you see Birtracks associated with these Young tableaus. Here is one that contains stuff only in a row. That makes a total symmetrizer. Here is one that contains everything just in a column, total antisymmetrizer. And these guys lead to something that have things that are symmetrized because they contain things in a row, and other things that are antisymmetrized because they contain things in a column. And if you want to have Hermitian operators. This was the PhD of Judy Osborne-Salinger. She found an algorithm to make these things with minimal effort. I started out, fell into this topic because I thought this is in textbooks. And what I found in textbooks was operators that were not Hermitian and not mutually orthogonal. I remembered I had seen textbooks on young tableaus and associated projection operators, but they were not, therefore, not mutually transverse, all manner of trouble. And then I found papers by Molin Sirdal and Stefan Debula, who had an algorithm to make Hermitian ones. But that algorithm produced objects that, in terms of Birtracks, were this long. I mean, longer, pretty quick. And therefore not very practical. Correct, but not very computationally useful on this level. And then we found, right, you see now in this example for S3, we found 3, these are the things that are underlaid in blue, Hermitian projection operators, and they look obviously Hermitian already because they are swap symmetric. And but there are only 4, and our algebra is 6 dimensional. Right? There's 6 permutation of 3 objects. Turns out that if you have young tableaus that have the same shape, that originated from the same young diagrams, there are Hermitian conjugate pairs that you can construct that take you, that in this case turn out to be unitary operators in the sense of our inner product, that turn this, that map one of these spaces into another one that belong to the same tableau. And if you do, and you can actually prove that this will always give you enough operators to span the whole algebra. So that was one of Judy's results. And so I call those elements in there T, I, Ij. I labels the diagram, and Ij labels the entry, so to speak, in this matrix where I arrange these guys. This has a connection with the matrix representation of the algebra that's very neat, but I'm not going to talk about this here. And the multiplication table of these is very, very simple. It says, as written on the right, if you have an element of these constructed objects, projection operators or transition operators, transition operators I call the guys that are put in the off-diagonal position, that take you from one space to another, then the product is non-zero only if the shape of the associated diagram is the associated diagram, shape of the tableau is the same. And I get non-zero only if the result, the resulting index L is the same as the entering index here, and otherwise I get either projection or transition operator that belongs, that falls into one of these things. And this shows you that these 4 form a closed subalgebra because that's their multiplication. These 4 in the box in the middle are a subalgebra. So we get a decomposition of the subalgebra. We also get a decomposition from the projection operators into irreducible representations of HCN in a moment. Because if I look at this by just taking the diagonal guys, the projection operator, the Hermitian operators in this list, turns out I get a decomposition of unity. Here is an example for S3. Right here are the objects that I had before. If I take them to act on Cn to the 3, I'm missing the power Cn power 3. That's what I'm missing here, because I'm acting on tensor operators. Apologies for that. Right? I have stacked 3 Cn's in a tensor product. Mistake here. But okay. Then I'm getting because the operators I'm acting on here are invariant on the SCN operation, I'm unable to take something out of this space from this space into that space by applying SCN. So I have decomposed my tensor space into invariant subspace. Now you need, this is a convenient way to find invariant subspaces in there. What you still need to prove is that, in fact, the subspaces that are obtained here are actually irreducible, and irreducible now means I cannot find subspaces in there that are smaller in each of those, that are smaller and still invariant under arbitrary SUN operation. But that you can prove. So what this gives you, this procedure gives you, is a decomposition into irreducible multiples. So you can apply this to what you're seeing in atomic physics and do all the Plech-Gordon series calculations in Birtracks, and it's pretty quick and pretty diagrammatically neat. Right. Now, how are we doing for time? Yeah, should be good. Now, let's look at SUN again and introduce Birtracks for objects that appear in SUN. I've talked before about the generators, and here I've left the eyes off because they are mostly not shown. They actually just also disappear from a product in a simple way if you want to. If you just use these generators. Right? I've talked about the adjoint representation where I act on the algebra element by conjugation, using the diagram. So I'm here doing it on the basis elements. And if I know that the result of this operation is a group element, I must be able to expand the result back out with real coefficients. And that you can do. Those real coefficients are known as the representation matrices of the adjoint representation. They're easy to calculate. But if you multiply with U inverse actually is just U transpose that you can show. Then you find, oh, these generators are invariants if I touch all of the indices, the matrix indices that U and U dagger act on, and the UAB acts on the basis label. And if I act on all of them appropriately, I'm not changing a thing. I can convert this into Birtrack notation and think about this in a very nice way by drawing a line with an arrow on it that carries the basis, the matrix indices of the generators, and I attach another line to the arrow, a dashed line here, that carries the index of the generator. In the end, of course, I will draw diagrams where I never write indices. I just draw the diagram. But from this definition, it's clear how to convert this back into something that contains these matrices, these generator matrices. I can form conjugates by flipping and reversing arrows. The generators are Hermitian, so nothing bad happens. And I can draw them like this. I can also draw my Kronecker deltas again, now with two lower indices by drawing diagrams like this with indices placed the way I've shown it. And then I can compute quantities. The way we've normalized our generators allows, so, right, what if I draw something like this? I have a generator here, I have a generator there, and I connect the indices over here to sum of them. Then this translates into, with the square root of 2, into 2 times trace of this. And this is the way we normalize our generators in QCD. Gell-Mann matrices with a factor 1/2 thrown in give generators that are normalized like this. They're orthogonal, right? That's what I already told you. Here I'm telling you what the convention for the prefactor in our inner product is. This is the inner product. If I do this, multiply my generator Birtrack with the Kronecker delta Birtrack, what I get is the trace of a generator. And remember, the algebra elements of SU n are traceless, so that diagram is an automatic zero. Once I know these two things, I can write down objects like this and immediately verify, oh, this is a projection operator. Can also verify that it's a Hessian very nicely. I can write down this object with a factor 1 over n here and immediately verify that's a projection operator. Because if you stick two of these guys together, well, okay, let me just write it on the board for a second. Right? This one is really easy to do. I'm just square this. So as a diagram, I'm drawing this, right? This is just a square loop. This is a closed loop. So this is two Kronecker deltas contracted. So this gives you the trace of a unit matrix in n dimensions. So this is n. And that's the normalization factor that shows up to make this a projection. The 1 over n. So this is the game I'm doing. And you see, you can also calculate dimensions. You get the dimension of the space you project on by tracing the projection operator. The traces of these projection operators are easy to calculate in this game. And for the first one, you find nc squared minus 1. For the second one, you find the minus 1. You find the 1. So if you calculate the trace of this is the identity on the tensor product of V and V star and V dual. That has to be n squared. So simply, on dimensional grounds, this is a decomposition of unit. Nc squared minus 1 plus 1. Here's nc squared. Solving this for the guy over here gives you something that has a name. It's called the field center. Because I built it into the diagram with the factor square root of 2. That works out automatically. So it's square, right? It's square. Let me do the square. No, you actually see it. It's square contains in the middle contains this, which is just the Kronecker. So I get the original thing back without needing an extra factor. So not everybody does this, but that makes more normalization factors pop up. So my diagrams for the generators contain the square root of 2, and therefore I don't get the extra normalization factors that other people very often run into. Yes.
How does the loop logic work for this network? The new loops would have this dash and also.
Yeah. Okay. Let me just square one for you. Let me do this. Very simple. Right. I square this, and you do see that the direction of the lines always nicely matches up. Now here you see something we've already calculated, right? That is just.
I get that. I meant when you said the trace gives you n squared minus 1 as the dimensions.
Yeah. So now you do this. Now you do this again, right? Now you close this up. And you close it up like this. And from there, you can get to the n squared minus 1 relatively quickly. I'm not gonna, because otherwise I can't do this afterwards. I'm running out of time. But this is not hard. Right. I need one other thing here. Another way of making useful Birtracks. And here I'm showing you an algorithm to turn group elements into color singlet states directly. The algorithm is it's best explained in an example. So here I'm lining up, I'm looking at, in general, at n QQ bar pairs. I take the group element of group elements of Sn and I'm turning it into color neutral sets. How am I doing this? Well, S3 is a good example, right? I write the identity elements and I throw back in all those usually suppressed one cycles. Each one cycle is turned into a Kronecker delta of the sort that I just introduced. Each two cycle is turned into a trace of TAs, and I stick two TAs on to get rid of the index and convert it into fundamental index. Again, and I do this for every group element, and you get a list that you see here. It's clearly 3 factorial long, and those are all color singlet states that you can find 3 QQ bar pairs. You can see that these things are invariant under SUN by just using the rules that I've shown you on the last transparency. It's really something that you can check by yourself. It's not terribly hard. Most of these guys are mutually orthogonal. It's not so nice with the last two because they aren't. But if I symmetrize and anti-symmetrize, I'm getting orthogonal states out that are related to structure constants. The antisymmetric piece relates to the FABCs, and the other one relates to BABCs. If you've ever seen QCD calculations, those guys will have popped up. Those are independent and, in this sense, orthogonal invariants. Let's look at another basis of singlets. And for this, the whole shebang with the Young projectors pays off dramatically. You just take any of the elements of the algebra, of the spaces of the algebra that I obtained from my Young projection and transition operators. I take any of these guys, call any of these guys P, you take it and you bend it around as a diagram. Now, if you follow the direction of the lines, you see the lines that come out on top, right? Yeah. So you will have quark lines and anti-quark lines at the bottom. You can turn them in. They're clearly invariants because the building blocks are invariants. You can normalize them, and now we have another set of color neutral states constructed in a different way. Exactly the same number, n factorial of them. So, two types of bases that are useful for different things. Let me connect this back to my two types of events and inferentiation. One of the crucial things is, when I was talking about jets, is collinear limits must work out. So I have three types of objects in QCD that I can force into being collinear. I can force quarks onto quarks, antiquarks onto antiquarks, quarks onto antiquarks, and gluons onto either. Or onto either, or gluons onto gluons, right? Those are the types of coincidence limits that I have available. Now, if I have quarks onto quarks, or antiquarks onto the antiquarks, then the Young projectors are neat because they know about symmetrized stuff, like things being in relation to each other. So those help to see immediately what the effect of having a quarks going onto quarks or antiquarks going onto antiquarks is on singlets. If I want to have quarks and antiquarks merging direction, the basis that I make directly from permutation, elemental permutation group, is very nice because it always has quarks and antiquarks next to it. So that works. For gluons, both bases work essentially equally well to expose structures in this. This is essentially the same game as simplifying the calculation in classical mechanics by choosing the right coordinate system. Say you want to directly have angular momentum conservation around a particular axis, then it pays to choose this as your z-axis because then your calculation. It's exactly the same type of argument that goes into this, although right, the mathematical overburden is a little more extensive. It also helps a little to talk about zero momentum emissions, but that's a couple of extra steps that you need to go through to actually appreciate that this is happening. I think the first one is plausible, right? From here. All of these things place conceptual challenges if you are designing things like event generators that are used right in planning and evaluating results at the LHC collider experiments. It's enormously important. They manifest themselves strongly in renormalization group equations. In the next seminar, you will see things like this being referenced by me or being explained by me, I hope. In proofs of factorization theorems in QCD. Factorization theorems are theorems that aim at separating a piece of a calculation that is perturbatively calculable from pieces that are not perturbatively calculable and therefore must be obtained from experiment. If you want to match up and learn about some perturbative features on top of perturbatively things that are fixed in 2 or 3 experiments, but then you need use theory to make predictions for more than that. All right, I think this is what I had here, and here is a list. These are clickable links for you if you ever want to look into a little more. Thanks for your attention. Any questions on that?
So there's that, so there's that matrix you showed where you turn these tableaus into Birtrack, the Birtrack operators. So diagonal operators and we have these transition and then we have these transition operators, and they have these, form 3 normalization. It seems to me that like this should be able to give you the index structure of the thing without taking you would also be able to think
so those are these normalization factors are calculable in principle. It would be nice if we had closed formally from the outset, which we don't have. At the moment, we need to calculate the operators and then square them and stack. Yep.
Is it easy to write down like an arbitrary end or like that kind of matrix, or do you say?
So this is a tricky thing, right? The group grows factorial, so there is a limit. So if you have once you have the projection operators, they can actually be stored with very little requirement of storage. So that's good. But calculating them involves n factorial objects. So individually, you go through all of them in one step. I have found a way of not needing the full multiplication function, which is n factorial squared itself, which is fast, right?
But it's algorithmically.
It's algorithmically clear. We have the algorithm. We will have the mathematics. So on that level, I'm just playing. We're just playing with. And we keep the memory down for the log for 6 or 7. It fits in memory. Right? And it's fast. As long as it fits in memory, it's extremely fast. If it doesn't fit in memory, it's nothing. So I'm playing with tricks. So I think I have tricks where I can go a little further up at the expense of computing time and then save the thing. That should work.
What's the physics motivation for going beyond the n is 3? Because I understand it's nice to have an expression which is a function of n.
Yeah.
But is it very useful to have an expression like, oh, I know what it is, 1, 2, 3, 4, 5, 6, 7. Then I don't know.
No, what the utility is in have it as a function of arbitrary.
So you want to see a pattern as a function.
You see patterns in it. What people use is the large and C limit.
Right.
All the time. So if you can compare very easily with the large and C limit if you have n as a parameter, right? So the large and C limit or n c equals 3 are of interest to people. And then you can make statements about, okay, is this a good approximation? Is it not? That's the key.
But in this numerical, or with this overlooking approach, so you would just be seeing the pattern for different ends, but you wouldn't. Would you be able to get an analytic expression, or you just kind of?
I would get analytic.
Or
The projection operators themselves have nothing to do with n. So inside those guys, there is no n. The NC pop out in traces in normalization factors of states. So when I normalize the traces,
then you
the states, I get NC. In the construction of the operators, for example, there is no NC. All right. Let's close this. Hey guys.